Hello, my name is Michael Swing.
And my name is Zaina Aouad, and this summer we have been working together on a project for Dr. Lin's Computational Chemistry Research Lab to construct and equilibrate the protein NARK. NARK is an antiporter that exchanges nitrate for nitrite ions across a membrane. In this lab, we use programs such as VMD, which stands for Visual Molecular Dynamics, and NAMD, which stands for Nanoscale Molecular Dynamics, to construct and simulate molecules in different biological environments. VMD allows us to visualize the protein, and NAMD contains calculations for the trajectory of the atoms within the molecule. Together, these programs allow us to observe the behavior of molecules computationally without the constraints of a traditional wet lab.
The simulation process involves a 5-step procedure as visualized in Figure 2b. We begin by taking a protein model and we run it through a solvation step. We then ionize it, minimize it, equilibrate it, and run it through a final production process. In terms of NARK, we initially began by generating and constructing a model of the protein using VMD. We then introduced water into the solution to solvate it within a water box and added a concentrated solution of 0.15 molar KCl solution to ionize it. This introduced potassium and chlorine ions into the solution to neutralize any regions of formal charge within the protein. This ionized system was then run through a 10 picosecond minimization step in which the protein was allowed to achieve a low energy state and conformation. As you see in Figure 2a, the initial energy state was high and dramatically tapered down to a low energy state at around 3,000 steps. This demonstrated that the minimization process was successful and that the protein was able to achieve a low energy conformation. Based on the trajectories of those atoms, we were able to input those files into an equilibration step. Our first of 2.5 nanosecond equilibration simulations introduced the constant temperature at 300 Kelvin, in which we equilibrated the protein at that constant temperature. Based on the velocities of the atoms and the trajectories of those specific atoms, we were able to input that into a second equilibration process in which we underwent a constant temperature and pressure at 300 Kelvin and 1 bar respectively to see how the protein were to react in those conditions. As you see in Figure 3, our equilibrated form of NARK is superimposed over the original crystal structure of NARK in orange. Our structure of NARK is more relaxed and demonstrates that our equilibration process allowed it to achieve a lower energy conformation state.
Over the summer, we've learned skills that have laid the foundation for larger protein membrane simulations that we'll be working on in Dr. Lin's lab. Specifically, the project we'll be working on focuses on the operating mechanism of the CLCF fluorine proton antiporter. We'll be constructing and equilibrating a model of this protein. The skills required to successfully construct CLCF include knowing how to use the command line terminal, editing files using VI text editor, and an overall understanding of the files that are needed for the trajectory calculations. In the near future, we intend on using these computational skills we acquired this summer to successfully construct and equilibrate a membrane-bound model of CLCF. Thank you, everyone.